Background. Airborne contaminants. In buildings, the quality of the environment is affected greatly by the presence of contaminants in the air. These contaminants can be divided into two categories. 1. Particulates, suspended solid matter including A. Dust, lint, and smoke, B. Tobacco smoke, C. Pollen and spores, D. Bacteria and viruses. 2. Gases, matter in the gas state mixed with normal air including A. Volatile organic compounds, a combination of a large number of organic gases lumped together for simplicity. B. Carbon monoxide. C. Oxides of nitrogen and sulfur. D. Radon progeny. Quantitative analysis of these contaminants requires measuring their concentration in the air and the size of particulates. Concentration is measured in units of mass of contaminant per unit volume of air in micrograms per cubic meter, or in units of volume of contaminant per unit volume of air in parts per million. The sizes of most particles of interest here are measured in micrometers. A micrometer equals 1/1,000,000th of a meter. For comparison, human hair diameters range from 40 to 200 micrometers. Respirable particulates, those that can damage lungs, range in size from about 0.5 to 50.0 micrometers. This table lists common indoor air particulate contaminants and their size distribution. Gaseous contaminants are more numerous and harder to control. Some originate outdoors, others evaporate from materials, and still others result from indoor combustion processes. Many are carcinogenic or harmful in other ways. This table lists some gaseous indoor contaminants. Scientific study of the indoor environment began in the late 1800s. Minutes of the American Society of Heating, Refrigerating, and Air Conditioning Engineers, or ASHRAE, from the early 1900s reveal complaints about air quality and ventilation. Research accelerated in the late 1970s when the oil embargo led to a heightened awareness of energy consumption, which spurred tighter building envelopes, a reduction of ventilation rates, and the subsequent emergence of such phenomena as sick building syndrome. Sick building syndrome is a set of symptoms such as headaches and malaise that appear when the victim is in the building but improve when he or she leaves the building. It has been shown to be related to inadequate ventilation combined with the presence of chemical and/or biological contaminants. Increased ventilation rates since that time and greater awareness of the effects of indoor air quality on human health and the primary causes of poor IAQ have reduced the occurrences of this syndrome. Contaminant control mechanisms. Source control. A seemingly obvious way to control indoor air contamination is to avoid allowing contaminants to enter the air by utilizing source control. Source control is minimizing the release or flow rate of a contaminant. If the contaminants are entering the indoor air by leaking in from outside, the solution is to minimize infiltration. Infiltration is unintended and unwanted leakage of outdoor air. It can be limited but not eliminated entirely by careful design and construction of the building envelope. Caulking. Important techniques include inclusion of low permeability materials and caulking. Indoor air pressure that is higher than the ambient pressure is also a way to limit inward leakage. If the contaminants are escaping from building materials, one control method is to choose materials containing less of the contaminant. If the contaminant is being released into the air by a specific process, such as cooking or a copy machine, a good idea is to exhaust air from the immediate local area of the source, and thus remove the most contaminated air. Filtration. Directly removing contaminants from the air is an effective control for some contaminants. Properly selected air filters are effective in removing particulates, for example, but gas phase contaminants are more difficult and requires special adsorption filters. The larger the particle, the easier it is to filter. ASHRAE has published Standard 52.2 that provides a method for testing and rating air filters. This standard enables designers to select filters for efficiency and economy based on the anticipated particle sizes for the project. As filter efficiency increases, the air pressure drop across the filter increases as a general rule. Increased pressure drop means increased fan horsepower and thus more energy use. A responsible designer must balance the sustainability of the need for clean air against this increased energy use. Dilution. The third method of control, and the one most emphasized here and in the LEED rating system, is dilution. The basic concept is to remove the indoor air and its airborne contaminants by exhausting them and to replace the air with less contaminated air from outdoors. The general term for this is dilution ventilation. One advantage of this technique is that it is effective on all contaminants, so that if the dilution of the most concentrated one is adequate, the probability is high that all are controlled. Ventilation can be used to flush out the usual contaminants listed in the tables we showed you earlier, and also to provide comfort cooling by diluting heat in warm weather. Note that ventilation with air from outdoors can often, depending on the climate, bring with it a penalty of additional energy required to heat, cool, humidify, or dehumidify it to room conditions. Dilution ventilation can be accomplished by mechanical ventilation driven by fans, by natural ventilation driven by wind or buoyancy forces, or by mixed-mode ventilation that uses both methods. We will examine each one of these methods in detail.